Welcome back. Last time we introduced finite differences, the Euler-Ford, the discretization, and diffusion equation. Today we will continue with the Fourier analysis of the discretization. We will introduce the Theta method to discretize the diffusion equation, and we'll look at the maximum principle. But before I do that, let me show you some of the solutions of last year's exercise. So last year we discretized the convection or advection diffusion equation for an unknown b, which is a function of z, the vertical coordinate, and time. So here's dB dt. This is ddz of a nonlinear advective term. Alpha and beta are coefficients, in principle constant, and then this is the nonlinear diffusion term. So it is, has 4 b's in there, b cubed. When you differentiate this through, you see that it's indeed a diffusion, and you bring it to the other side, you see that it's a diffusive term. It's a model of magma going through a crack. So the crack comes lateral out of the page. It has a width as function of the vertical coordinate z, and it's fed at the bottom by a magma chamber, and at the top it erupts. So this equation has certain traveling wave exact solutions which look like this. So this is implicit in 9. It's implicit description. It gives z minus ct. C is the traveling wave speed. It expresses z minus ct minus also some reference constant as a function of b, this complicated function. So it's not possible. So implicit description of b, because there is no explicit description of b, at least I'm not aware of one. Now the solution, the numerical solution, is displayed here in this panel. So that's a explicit forward Euler discretization. The numerical solution is in blue, and the exact one is the dashed dotted line. So the exact one is basically 9, and the blue one is the numerical solution of 5. And this is the vertical coordinate on the vertical axis, on the y-axis if you wish, but it's the z-axis, and then b is on the horizontal axis, such that it matches this. Usually you would put the variable on the vertical axis and the coordinate on the horizontal axis, because here the axis is the vertical. We plot it like it would look in reality, so that it matches this. So let's run it. It's a movie. Oh, where do I put this? Maybe I want to make it a bit bigger. Does that work? Yes, that does work. I want this thing out of the way. Well, it's not going out of the way, but you'll see. There it goes, and it loops all the time. Let me march through by hand. So I put in some initial profile, and it generally marches through. What you do see is that the front is not very well captured. You need a front capturing scheme, or simply a lot more resolution, and then it oozes, it diffuses a bit out numerically beyond the front. So I didn't put in that much resolution. This is the step delta set, just to show you the difference between the numerical solution and the exact solution. Here you would need a lot more grid points, or a front following numerical scheme, which is more difficult. So we can march through. So you could make one of the tasks was to make a comparison between numerical and the exact solution. So here the front hasn't reached the top, and then it marches forward, and then at the end it reaches the top, and then now you see actually that the numerical and exact solution, because there's not that much variation, match very well. So in the end, the numerical solution catches up once the front has marched through, and the magma has erupted at the surface. Well, this was just a introduction. Let's go to the actual lecture. So I put that forward, so this can go in the background, this can go in the background, 3 can go in the background. So that's it. All set up. Show my face again. A bit smaller. So we focus on the electronic whiteboard. So last time in the last video lecture, last real lecture, we finished with the truncation area, and we saw that the Euler forward discretization was the first order discretization in time and the second order in space. And Taylor expansions are an important tool in that analysis. So now we will look at section 2.7 of Morton and Mayers, the Fourier analysis. Of the error. So a recap of the finite difference scheme we looked at. This is the capital U, right? So that's the approximation, as opposed to the real U discretized at grid point J and spatial grid point n times mu. So mu was delta t over delta x squared. So capital U n j plus n. So this is a 4-point stencil that uses un plus 1 in the future, unj is the one in the middle, and uj plus 1 and uj minus 1. So this one and this one at the side. So the stencil is, if you do it, this is this one, this one, this one, and the future. This is n plus 1. N plus 1. This is n. This is j. This is j plus 1. This is j minus 1. So it's a 4-point stencil. Uses 3 points of the stencil in the past and 1 in the future. Assuming periodic boundary conditions, so BCs, you can lift that, see Morton and Mayers, but let's assume that it's periodic. But it means that the domain, when you leave the domain on the right at x is 1, the signal comes back at x is 0. You literally wrap around a piece of paper. It's periodic. Then we substitute the ansatz for the approximation lambda to the power n. So this is now power, as opposed to a superscript index, times e to the power ikj delta x, where j we are familiar with, delta x, I squared is the imaginary number, so I squared is minus 1, and k is a wave number. Wave number, and we're familiar with delta x, and we're familiar with j because we introduced that into cross here, and we also recall that xj is j delta x, so this is xj. Recall so this is conform. Recall that for the real u of x as t, we could for example substitute a of t I kx, and if we substitute x is xj, then we see that we get this exponential here, and this amplitude a of t is replaced by lambda to the power n. So this is what you would do in the partial differential equation if you look at waves or other matters, and this is what you do, substitute. This substitution you make, so u and j is lambda to the power n e to the power ikj delta x. You put in the difference equation. So note that un plus 1j is lambda times unj, because you get lambda to the power n plus 1, which is lambda times lambda n, and therefore that's the case. And also this recognition saves one e to the unj plus 1 is e to the power ik delta x. You take out the 1 times unj, etc. So also unj minus 1 is e to the power minus ik delta x times unj. That means you can factor out the unj. Since the cross equation is a linear equation, that makes actually the arithmetic of substitution and analyzing a lot easier. So what do you get? So check this. What do you get? You get that lambda, that one remains, is 1 plus mu e to the power ik delta x minus 2 is plus e to the power minus ik delta x. Check this. I'm not going to do it. If you use this note, you see that comes out of it pretty quickly. This is 1 minus, using cardiometric rule, 1 minus 2u, 1 minus cos k delta x. That's easy to see. You take out the 2 and then you see that and you put the minus in, you see that that's the case, and this is 1 minus 4 sine squared k delta x over 2. Lambda is now seen to be a function of k. Lambda of k is the amplification factor. So let's see for which k it's the worst. So for k is m pi with m an integer, we obtain unj. We can actually wrap it up, so it's m. So we obtain we can write unj as the sum of whole range of solutions. We can introduce an amplitude. We get e to the power I m pi j delta x lambda m pi, so k is m pi to the power n. Generally, and this is very important, generally lambda is complex. So lambda is the real part of lambda plus imaginary number times the imaginary part of lambda, with I squared is minus 1, as I said. Stability requires that the modulus of lambda being complex is the modulus of lambda we look at, is less or equal than 1. So why is this a requirement for stability? Well, let's go to the ansatz. The ansatz has lambda to the power n. If the modulus of lambda is complex, if the modulus of lambda is bigger than 1, and you raise it to a power, then generally or eventually lambda will run away and become infinite. For large enough, and so it runs away. So unless there is anything in your equation your partial differential equation accommodating that kind of explosive runaway. You don't want that, so you want for stability that the modulus of lambda is less or equal than 1. Hence, the case with sine squared k delta x over 2 is 1 is the worst. So you pick the wave number so in here you pick the k, which is the worst, which is the case for which sine squared is 1. For mu is positive, so we're going to look at the case where lambda is less than -1, then the modulus is bigger than 1. So we take that one, so that lambda, modulus of lambda less or equal than 1 is then equivalent to using the previous result, 1 minus 4 mu is less or equal than 1, so mu less or equal than 1 is the stability criterion. Let's go back. This becomes 1 minus 4 mu. And we look at the case, it will become unstable for 1 minus 4 mu less than -1. So lambda is 1 minus 4 is less than -1, then mu is bigger than half. Is unstable. So mu less or equal than half brings us stability. With mu is half, meaning that lambda is -1, so the modulus of lambda is 1. So basically we looked at the case -1 less or equal than 1 minus 4 mu is equal than 1. So -1 less or equal than 1 minus 4 mu. So mu less or equal than half is the stability criterion. Let's go up. So mu was delta t over delta x squared. X squared needs to be less or equal than half. So that gives you, given delta x, that gives you a time step criterion. If you provide delta x, it gives you a delta t for which your numerical scheme is stable. Look at figure 2.2 in Morton and Mayers. Conform figure 2.2 in Morton and Mayers, and it asks you for today to reproduce that figure in a Python program, and now you understand with this stability criterion why for one delta t used in that simulation the scheme is stable, and in the other case lambda is bigger than 1, modulus of lambda is bigger than 1, and it blows up. So that gives, once delta x becomes very small, delta t becomes extra small because the criterion involves the square of delta x. So that means that your time step is very, very small and becomes very, very small in an explicit scheme when you increase the resolution. So we're looking for a better scheme. And that better scheme is an implicit scheme, comes at extra computational cost, but you can lift some of the time step description, and we're going to introduce the Theta method. So it's a 6-point stencil. So this is n plus 1, this is n, and this is j plus 1, j minus 1. We're going to use 3 points in the past and 3 points in the future. So the Now, so using the difference notation introduced in the last video lecture, namely that delta x squared u of x comma t, so delta sub x squared is u of x plus delta x comma t minus 2 u of x comma t plus u of x minus delta x comma t, which you can also apply on at the approximation. Then we get for the theta scheme the following. So it's un plus 1 j minus un j. So if you divide that by delta t, you have the du dt approximation is mu, which is delta t over delta x squared. So I already took the delta t to the other side, and now you take away theta in the future and await 1 minus theta in the past. And for the homogeneous boundary conditions, the index runs from 1 to what is it? J minus 1, because at j is 0 and j is capital J, we have our homogeneous Dirichlet boundary conditions, and we take the weight theta line between 0 and 1. Now for theta is 0, 1 minus theta becomes 1, and that means that we only have terms in the past. Now recall that this delta x squared of u and j, and likewise of u and j minus j plus 1, is un j plus 1 minus 2 u and j plus u and j minus 1. So that's the difference stencil of the second order operator. So this is approximately delta x squared times uxx. And this was, recalled, delta t times du dt. But I've divided through by delta t, and I've taken out here the delta x squared is in the mu. So theta is 0, gives us the explicit forward Euler scheme, which we already introduced. Theta is 1. So for theta is 1, we see that there is no term in the future, but only no term in the past. I mean, 1 minus theta is 0. And for theta is 1, this term theta times delta x squared times un n plus 1 j is exclusively in the future, and it's the implicit scheme, implicit backward Euler scheme of paragraph 2.8. This is, I should have put the word Euler, forward Euler, in there. So now the only problem is here, I have unknowns here, but I have also unknowns here, because they're time level n plus 1. I don't know those yet. So bring all unknowns to the left hand side. This is actually 2.75. That gives us 2.76 in Morton and Mayers, minus theta mu un plus 1 j minus 1 plus 1 plus 2 theta mu un plus 1 j minus theta mu un plus 1 j plus 1 is 1 plus 1 minus theta mu delta x squared. So I keep the delta x squared notation there because it's nice and compact. Un j. So this, on the left hand side, we have a diagonal matrix. If we put all the unknowns un plus 1j into a column factor of length j minus 1. Now a Fourier analysis can be done of 2.75 or 2.76 using again the ansatz un plus 1j is lambda to the power n e to the power I k j delta x, and then we get lambda minus 1 is mu theta lambda plus so the lambda comes from the un plus 1 term on the right hand side. The 1 comes from the un j term on the right hand side, which I put to the left hand side. The theta term had everything in the future, so picks up 1 lambda. The 1 minus theta term in the past doesn't pick up anything because it's at unj, and then I pick up these terms from the just normal stencil. We saw that one before in the analysis for the forward Fourier analysis of the forward Euler equation. And this we can factor again as mu theta lambda plus 1 minus theta, and this becomes minus 4, using the same goniometric rules, delta x squared over 2, and now we have to rearrange in terms of lambda. So lambda, we put all the terms with lambda, so it's this term and this term multiplied by this term. We bring that to the right hand side and divide through, so 1 minus 4, 1 minus theta, 1 minus theta, what is it, sine mu sine squared k delta x over 2, so that's this term minus sine times 1 minus theta, so this one, divided by 1, the one we already have on the left hand side. So this one here goes to here, and this becomes 4 theta mu, so the minus sign brought to times theta lambda mu brought to the left hand side becomes a plus sign, so that's why this is a plus sign, and this is sine squared k delta x over 2, which is always less or equal than 1, because the denominator is less than 1 and the denominator is bigger than 1. No, we want this to be less or equal than 1, so now we have to analyze. It's not always less than 1. You have to look for theta. Since I'm going to hide on myself. Since mu is bigger than 0 and 0 less or equal than 0 less or equal than 1 less or equal than theta, we find actually this is correct. This is always less or equal than 1, so lambda is always less or equal than 1, never bigger bigger than 1. The question is now, so look at, and also notice that in this case lambda is real. So in general, given the ansatz, lambda is complex, but in this case, because it's a symmetric scheme, it's real. So now look at the case for which lambda less or equal than 1 and the modulus of lambda is bigger than 1. So this would be unstable. That means that 1 minus 4, 1 minus theta times mu sine squared k delta x over 2 is less than minus 1 plus and so I fill in lambda and look at that. So 4 theta mu sine squared k delta x over 2. Then we need to rearrange that. So the best thing, what's the best thing to do? The best thing is to bring this term to that side and then read it from right to left. And this minus 1 you bring to the left hand side, but then you read it from right to left. Then you get 4 mu 1 minus 2 theta times sinus squared k delta x over 2 is bigger than 2. So the less, so when I read it from right, when I rearrange, bring this term there and this term there, I get a 2. So so then the rearranged term, this plus this term, gives me, so that gives me 4 times 1. That's 4, so that's actually gives me the 1, so that 1 is there. The theta, that's plus theta, on the other side becomes minus theta, so that's why I have minus 2 theta like here. So this, there's instability when that's the case. So take the case k delta x is pi, then we get mu 1 minus 2 theta is bigger than half. That gives the unstable case. So the scheme is stable for theta bigger or equal than half, and this is 2.78 in Morton and Mayers. Since then 2.78 cannot be met. So let's see how that works. So 2 is bigger than half, then if theta is bigger than half, this becomes negative. So that's right. So b bigger than half, it's half, it's 0, then it can't be met. So for 0 less or equal than theta less or equal than half, it's stable when not the bigger sign holds with the lesser equal than sign. So it's stable when mu is less or equal than half 1 over 1 plus 1 minus 2 theta. 1 minus 2 theta. So for half less or equal than theta less or equal than 1, always stable for every mu. read the rest of section 2.10 regarding truncation, the truncation error, and some numerical tests. For theta is half, the theta method is the famous Crank-Nicolson scheme. It's quite a nice paper, which is second order. So the theta method is again order delta t, so first order for the time stepper, and order delta x squared in space, except for theta is half, so that's the Crank-Nicolson scheme. Then it becomes, due to the symmetry, order delta t squared, that's incorrectly written, order delta t squared and order delta x squared, so that's the second order scheme. And theta is half is exactly at the point where the scheme and it's unconditionally stable for theta is half, because theta is half was between half and 1, the scheme was unconditionally stable. So now let's finish off with the maximum principle. Read this paragraph. I'm not doing it justice. Read that section. Maximum principle and convergence. Holds for mu times 1 minus theta is less or equal than half. So this is a more stringent condition than the stability condition. So the generic question to be answered here is, what is the convergence of the theta scheme, which of course includes the backward Euler and forward Euler scheme, for the diffusion equation with homogeneous boundary conditions, in the case that delta x and delta t go to 0 under this condition, because this links delta t and delta x. So that gives us theorem, and I'm just stating it, so we're going to use it as such. 2.1, the theta method 2.75 with theta between 0 and 1, and this condition, this maximum principle condition, mu times 1 minus theta is less or equal than 1/2, yields u and j, the numerical solution, satisfying u min less or equal than un less or equal than u max. So there is a minimum u min and a maximum u min between which un j remains, where these are, this u min and u max, is the minimum of the initial data of the the boundary conditions. Boundary condition this must be m then, u not j for 0 less or equal than j less or equal than capital J, and the boundary condition at the other side, 0 less or equal than m less or equal than n. So these are the boundary data, the minimum of the boundary and data and the initial data, and u max is the max of basically the same argument. It yields for these conditions that for any refinement path and data on 0, 1, the domain, and the domain in space and the domain in time, 0, 2, f, that the truncation error, in this case the truncation error is Tn plus half j, Tn plus half being a more convenient spot, that this goes to 0. So you get, so the method under that condition, so this condition converges. So that's very important. You're guaranteed that it works upon this refinement. So let's sketch now. So let's now make two sketches. So this is t, this is x. So the boundary data are there. So the boundary condition is the initial condition here. Anything which happens in here on the grid, so that's u and j, lies between the minimum on the boundaries and including the initial conditions and the maximum found on the boundaries and as initial condition. So there's a u min here somewhere, and there is a u max somewhere on this boundary, and u and j is guaranteed to lie in between there. So let's now plot mu versus theta, 0, half, 1. So this is mu. Then this, if this is half and this is 1, well, half, 1 doesn't really matter. Half, then this is half, then this is mu is half. So this is the Fourier stability boundary, and the other one is it comes from half. It needs to be a bit more tighter like that. And the other one is the asymptotes the other one is the criterion for the maximum principle. You see that theta is 1, this asymptotes, and this asymptotes is theta is half. So here the scheme is unstable. Here it's stable, but it doesn't satisfy the maximum principle. Stable plus convergent. So depending on what you want numerically, you either want to be stable and convergent, only stable, and unstable you never want to be. So, and this is the axis theta, where theta lies between 0 and 1. Right? So this is the stability criterion. This is for a specific case of homogeneous boundary conditions. For other boundary conditions, there are slight changes, as we will see in the exercise. So thank you very much. Long lecture, but so be it. It's very important to read paragraph 2.11. That gives you the full flavor and the proof of the theorem. I'm not going to give the proof in the lectures. Thank you very much.